let's look at the application of the first order conditions to actual calculation questions. So now I'm looking at page 4 of slide 5-1. Okay, example 1. So this function is minus 2x squared plus 24x minus 20. So let's first look at this function as a quadratic. And here a equals to minus 2, b equals to 24, c equals to minus 20. So in this case, a is smaller than 0. That means this function should be opening downwards, right? Therefore, there is a maximum for this function, okay? So the optimization is actually maximization in this case. Then, how can we find the x that maximizes this function? The previous knowledge tells us we need to solve the vertex, which is minus b over 2a. In this case, is minus 24 over 2 by minus 2. And the 2 minus signs cancel. So that is 24 over 4, which is 6. Okay, so here, when x equals to 6, this function is maximized. Okay, so that's when we utilize the quadratic feature of this function. Then let's utilize the first order conditions. So the first order conditions is to set up the first order derivative under the condition that the derivative equal to 0. Okay, so first we need to work out the left-hand side of this equation, which is prime. Okay, that is minus 2 by 2x plus 24, which is minus 4x plus 24. And then we are to solve for x so that this equation holds. That's minus 4x plus 24 equal to 0. So 24 equals to minus 4x. Move to the other side, change its sign. So x equal to 6. So now we know when x equal to 6, this function is optimized, right? And the second step is second order conditions. To check the second order condition. So here, the second order derivative is the first order of the first order. So we are taking derivative with respect to minus 4x plus 24. With respect to x, the result is minus 4, smaller than 0. This function is concave. Therefore, when x equals to 6, fx is maximized. Because for a concave function, it's like a cave, and we have a peak for this. Okay, so now we approach to both, to this question from both methods. Now that we are here, I'd like to give you a further point out. So previously, for quadratic, okay, the function is ax squared plus bx plus c, right? And we say the vertex where the function is maximized or minimized, right, is found by x equals to minus b over 2a. So here I would like to show you how this vertex is found. This vertex is actually found by first order conditions. So what is the first order derivative? Here in this case, that is 2ax plus b. That's the first order derivative of fx. And solve the x when the first order derivative equal to 0, that is 2ax equals to minus b. So x equals to minus b over 2a. So here our habit is to add a star on x if this is the x that maximizes or minimizes this function. And how does x maximize or minimize this function? it is dependent on the second order derivative. And the second order derivative in this case, which is to take another derivative with respect to the first order, which is 2ax plus b. The result is 2a. And here you can see if a is greater than 0, f double prime x is greater than 0. Here we have a minimum because that's a convex, right? A is smaller than 0, f double prime x is smaller than 0, we have a concave, so the relative maximum is a relative extremum is a maximum. And that coincides, that matches with what our finding graphic understanding when x is greater than 0, it is opening upwards, right? So there is only a bottom. When a is smaller than 0, it is opening, the function is opening downwards with this graph. Then we have a peak, which is maximum.